Hi. My, my name is Manish. Today I'm going to talk to you about compilers. So a bit about me. I work at Mozilla on the Servo browser engine. Yes, that is our logo. It's technically unofficial, but like, don't tell anyone. Anyway, yes, we have a Doge for a logo. I also contribute to the Rust community and the Rust compiler. Rust, it's a programming language that tries to empower everyone to build fast and reliable and secure systems. Rust is a compiled language. In compiled languages, you have a compiler program that takes the source code that you write and converts it into machine code that the compiler can understand, that the computer can understand. Compilers are a fundamental tool that we use to build programs and work with computers. I think compilers are really, really cool. Compilers are what compile our program, but where do they come from? Who compiles the compiler? I mean, we had a compiler here last time, so it's got to be some other compiler, right? That means it's like compilers all the way down, I guess? I don't know. For many languages, it's not just that you need a compiler to build that compiler. You need a compiler for the same language. The compiler for your language is written in the same language, which somehow makes sense. I promise you it does make sense eventually. The Rust compiler is written in Rust. Many C++ compilers are also written in C++. GCC is written in C++, for example. So such compilers are called Bootstrapped compilers. The way their development works is that you can build a version of the compiler with an older version of the compiler. So for example, if you want to build the latest Rust compiler, which is I think 32, you need the previous version of that. If you want to build this, you need that one, and so on, all the way back. Whoops. Oh no. Yeah. Similarly, if you want to build GCC, most C++ compilers from the last 10-ish years will work. Eventually, this chicken and egg problem has to end up somewhere, right? You can't just go compilers all the way. There's something at the bottom. So it turns out that this is where the bootstrapping comes in. Bootstrapping comes from the phrase, like, pulling yourself up by your own bootstraps. And what happens is that initially you start writing a simpler compiler and then add complexity to it as you go forward. So when Dennis Ritchie, for example, wrote the first C compiler, he actually wrote a compiler for a much simpler language, which I'm just going to call C0, in assembly. Assembly is this language. It's a human-readable version of machine code, and machine code is what computers can understand. So he wrote a really it's hard to program in assembly, but you can write a really simple compiler in it. So he wrote a really simple C compiler in assembly, and he used this assembler, which is a simple program that converts assembly to machine code, to get the first compiler for this subset of C that I'm calling C0. Then he wrote another compiler for a much more better compiler for a language that I'm going to call C1 that was written in this subset C0, and he used the compilers that he had to build to compile this one. And now you can add features to this and write a better version of that, and compile a better version, and then you can add more features, compile it with the old one, and keep doing this until you finally have a compiler that supports all the features you wanted. This takes a while, but you eventually get to a C compiler. Newer languages don't actually do all the way up to the top. What they often do is that they'll start with a compiler written in a different language that already has a compiler, and then at some point, once it's mature enough, switch over to being bootstrapped, and then initially you can use that other compiler to start. So the Rust compiler was initially written in a language called OCaml. Have you ever thought about how much we trust the tools we use? In 1984, Ken Thompson gave a talk about this attack and about the nature of trust in our systems. And he focused on a very, very fascinating outcome of this whole bootstrapping process. of the fact that your compiler is written in the language that it compiles. He first talked about how it's possible to make a compiler malicious. Let's say you have a login program. It'll probably have like some function like check password that takes your password and, I don't know, checks it against some list of what the passwords are allowed to be. Now, you're compiling your program, you're compiling this login program using your compiler and using it on your system. And that's fine, except someone can, what if the compiler was changed so that when it finds this check password function, it actually adds a backdoor to the function. This kind of function, this backdoor could be something like, oh, if the user types in this password, always let them in. And now the login function suddenly lets you log in as anyone as long as you know the secret password that the compiler just inserted in the program. So this means that if you want to trust your program, you have to trust the compiler that you're using to build the program. Okay. If we have to do that, I mean, we have our compiler source code. We can just build our own compiler. We have the source code, we just build it. But wait, that's also compiled by a compiler. That compiler could also do things to our code. So you have the same problem. Since you need a copy of that compiler to build a copy of your compiler, someone can backdoor the first compiler, that compiler copy, so that it inserts itself into the copy of the compiler that you're building. You're now forced to trust your code. So for example, here you can change the compiler so that it adds the same backdoor, but it also finds the function that compiles stuff in the compiler and adds this whole backdoor to itself. And then you can compile a compiler whose source code is all nice and clean and free of backdoors with this broken compiler and get a bad compiler out of that. And that will continue forever, as much as you use that compiler. So now you're kind of forced to trust your tools. And this attack is called the trusting trust attack because of the name of the original talk. So when I first heard about this, I was really intrigued. Compilers have this so it turns out compilers have this weird chicken and egg situation where they're built with themselves and somehow that works. And furthermore, you can abuse this to insert backdoors that don't even show up in the source code, that they're just like ghosts in the compiler. So this really, really got me interested in compilers. At the time, I didn't really understand how they worked. I just understood that they're weird and cool. So a personal goal I gave for myself back then was, one day I will actually do this for myself. And then I kind of forgot about it, but it's fine. Many years later, I had become a contributor to the Rust programming language. So now I actually knew how compilers worked. And I realized, I thought about it for a bit, and I was like, oh, this is actually not that hard to do. So I tried doing it. It's worth understanding how compilers kind of work to understand this attack. This diagram is a very simplified pipeline of how most compilers work. So first, you have your source code. It parses the source code that you give to it, and it turns it into a more structured format. It's often called a syntax tree. Then it'll look at the syntax tree and find what things are referring to what things and link things up. Like if you have imports, it'll find out where the imports came from, things like that. That's usually called name resolution. Then it'll run a bunch of checks, like type checking, for example, checking if all your types match and everything. And once you know that your program is correct and you have all this structure about it, you can now restructure the program to optimize it and convert it to machine code, which again, the computer understands. In the Rust compiler, these last two steps are handled by a different library called LLVM. So as you go further down this pipeline, things get more and more complicated. Here you start out with just the source code. Here you have a very nice structured format of the source code. And now by the time you're here, you have that structured format, plus you've got like a billion other things that depend on that. So poking at that structured format might mean invalidating other things. So when I wanted to pick where to stick this attack, I decided to put it right after parsing, because then I have a very nice structured representation that I can work with, but I don't have to deal with all that other stuff that's floating around that I might break if I change things. All right, So my first step was to insert just some backdoor into the compiler, not the weird loopy trusting trust backdoor, just some backdoor. I didn't want to do the entire attack at once because I wasn't yet sure how to do it. I instead wrote a very simple backdoor that replaces strings that say hello world with the equivalent in my native language, which is Jagala Namaskar. Apologies to the transcriber. When I wrote this talk, it didn't occur to me that I'd have to deal with that. So a program that prints out hello world when compiled by my compiler will instead print out Jagala Namaskar. The code in this slide is pseudocode. So the code in this slide is pseudocode. The actual compiler code is a bit more complicated, but it's only complicated because the compiler has all these structures and stuff, and I've simplified it for this purpose. But the idea is the same. So, and if you want to look at the actual code, I'll link to a blog post at the end that contains the actual code. So I first found the part of the compiler that handles the step right after parsing. So I'm just going to call it after parsing here. It takes in this structured representation, this syntax tree of the program, which I'm just calling program here, and it does some other stuff to it. I added a line to that that's just called this function add backdoor on this program. And I passed this variable to this add backdoor function up there, which I also defined. In this function, I basically iterate through all of the expressions in the program, and I find expressions which are string literals that say hello world, and instead I replace them with a new string literal that says Jagala Namaskar. All right, the next step is to make the backdoor add itself. This is where it gets interesting. We can iterate through all of the functions in the program. We can, looking for the function after parsing that we've just added a line to, and we can add this function call of add backdoor to that. But now we need to insert this add backdoor function itself. How do we do that? We don't have it. If we wanted to do that, we'd need that function as a string inside itself. But then that string also needs to be inside that string, which needs to be inside that string, which needs to be inside that string, and this is terrible. So we need a different solution. Some of you may have worked with things called quines. This is something similar to what happens when you try to write a quine is a program that prints its own source code. These are really fun to write. You should try to do one sometime in your favorite language. These are kind of tricky to construct. Because for the same reason, if your program is printing its own source code, it needs to contain a string that contains its source code. That string then needs to contain that string that needs to contain that string. And again, this is terrible. This makes your program infinitely large. With quines, there's like a trick to get around this, which is that you use a variable. So this is our quine. We first create a variable that contains the second line. Don't look at the contents, it's just the same as the second line. As you can see, this is just the second line. In the second line, we do two things. We first print out the line that sets the variable itself. So now we're printing out this first line. And that's done by, we can just reuse the variable because we're just printing its contents after setting it to a variable. And then we print out the line that's actually printing the program, which is the second line. So all we have to do is use the variable twice, and now this program isn't really large. If you really look closely at this example, this is Python code, but it doesn't quite solve the problem because you still need to deal with escaping. And there are various ways to fix that problem, but it depends on the language, and it's not so relevant. The core insight is that if you set most of the code to a variable and then use that variable twice, once to set the line that sets the code and once to print the rest of the code, you can create a quine. And really, we can use the same trick here. We're inserting the backdoor, and it's kind of like printing, but we're doing a bit more work. So let's try what we've learned to our attack. We now have a variable, which I'm calling program string at the top. And it contains all of this code as a string. It's not on the slides because it would get too big. And this is all of the add backdoor function, but it doesn't contain itself. It just contains this function. When we find the after parsing function, just like last time, we add the function call to the add backdoor function. And then we do two things. First, we parse this program string line to insert the add backdoor function. Like this entire function is contained in this string. So if we parse it and we insert it, we get this function in our code. And then we create the line that actually sets this constant. We're just creating this line, and we just reuse the variable to create its own contents. And then we also insert that somewhere. As you can see here, we're using this variable twice. We first use it to insert the function, and then we use it to insert the line that creates itself. While I did this with the Rust compiler, most compilers work really similarly, and it should be possible to like replicate this attack with mostly the same features with a compiler of your choice. This attack is a really fun way to learn more about your compiler. I highly recommend trying it out if you're interested in playing with a compiler. Just pick one and like find where it parses stuff and look at things, and you'll eventually get something. Anyway, compilers are really, really cool. I hope this talk motivates you to start poking at compilers, hack on them, maybe write this attack, or maybe write a feature that's useful and not an attack. Both are fine. I like the attack one more. I've really enjoyed my time hacking on compilers, and I hope you do too. Thank you.